Okay, the topic we are going to cover in today's lecture is power method. Now, we use this method particularly to find actually not find, but rather approximate the dominant eigenvalue and corresponding eigenvector also of an n by n matrix. So let A be an n by n matrix, and probably it has eigenvalues lambda 1, lambda 2, up to lambda n. Of course, we can have repeated eigenvalues, but I have considered those repetitions as well. That is why I wrote exactly n eigenvalues. Then, in particular, lambda k is called the dominant eigenvalue of A if the following condition is satisfied, which is lambda k absolute value is greater than absolute value of all the other eigenvalues where I runs from 1 to n and I is not equal to k in particular, of course. Okay, now from this definition, you should be able to understand that not every n by n matrix has a dominant eigenvalue. Why so? Let me show you by an example. For example, consider the matrix A 1 0 0 minus 1. I have intentionally chosen a diagonal matrix so that we can clearly see what the eigenvalues are, right? So it has eigenvalues lambda 1 equals to 1 and lambda 2 equals to minus 1. And you can clearly see that both have the same absolute value. In this case, the condition in the definition in our last page is not satisfied. You should be able to see that. It says that we must have strictly greater than. So technically, we have a tie here, and according to the definition in this last page, tie is not acceptable. So this particular example, this particular matrix A does, even though it's a square matrix, but it does not have any dominant eigenvalue. Then comes dominant eigenvector. What is a dominant eigenvector? It's actually the eigenvector corresponding to the dominant eigenvalue. There no such thing as the eigenvector having max magnitude or anything like that. There is no concept of that. It's simply the eigenvector that has the that corresponds to the dominant eigenvalue. Now let me show you an easy example that involves the power method, because power method actually is a numerical technique to find the approximate dominant eigenvalue, and it's an iterative method. So the algorithm actually consists of an iterative equation, and the equation kind of looks like the equation involved in fixed point method. So let me show you by an example. So we have a matrix A equals to 2, minus 12, 1, and minus 5. So what we are going to do is use the equation x1 equals to basically kind of xi plus 1 equals to axi. This is the iterative equation we are going to use. And we write for I equals to 0, the first equation is x1 ax0. Now the question is, what is x0, the first initial choice? It's up to us. The very safe choice would be just 1, 1. Let's just stay with me and go through the process. All right, so let's multiply. So a is 2 minus 12, 1 minus 5, and x0 is 1, 1. So the result is 2 minus 12 is minus 10, and 1 minus 5 is minus 4. Now let's repeatedly use these equations. So x2 is simply 2 minus 12, 1 minus 5 times minus 10 minus 4, and this result is 28, 10. If we go on like this, we get x3 equals to minus 64 to minus 22. We get x4 equals to 136 and 46. Let's move on to the next page. X5, we shall write 6 iterations. X5 is minus 280. I have the calculations done in front of me. That is why I'm being able to write them without loss of any terms. 6 is 568, 190. Now, there is basically no sign of any kind of convergence which is required for any iterative method, right? You cannot see any hint of any kind of convergence so far. But then again, an eigenvector can be scaled, right? So what we are going to do is write this as, take the minus 4 as common, then we get 2.5 and 1. Do the same with this. Take 10 out, we have 2.8 and 1. So what we are doing is taking the number at the bottom out of the matrix every time. So this becomes minus 22, 2.911, 1. This becomes 46, 2.98, sorry, 96 and 1. On the next page, this becomes, take minus 94 out. So we have 1 at the bottom, and on top we have 2.98. Finally, 190, we have 2.99 and 1. As you can see, after scaling, or after actually taking the lower guy out of the matrix, we can see that the process makes sure that we have 1 at the bottom every time. Just follow to the top guy in each matrix, and you can see that, you can see that we have 2.5 here. On the next iteration, we have 2.8, then 2.91, 2.96. And you can see that it's converging to a certain value, and that value looks like 3. So our conclusion is, even though we know it's converging to 3, but at the last iteration, we got 2.99, and we probably would get 2.99 again for x7 and x8, etc. So maybe up to 2 decimal places, this is the best we can get. Not really, at least, I think at some point, after some finite number of iterations, it will eventually get to almost 3. But let's conclude with 2.99. What we are going to conclude is the dominant eigenvalue, eigenvector is 2.991. Or if you choose to write 3, 1, that's okay by me. Okay. Now, this is the algorithm to find, this is the iterative algorithm to find the dominant eigenvector. But what about the dominant eigenvalue? Basically, the definition of dominant eigenvector is dependent on the definition of dominant eigenvalue. We should get the dominant eigenvalue first. That was our first impression, right? But we got the dominant eigenvector, but we have a formula called the Rayleigh quotient, which gives us an equation like this: lambda equals to ax dot x by x dot x. Basically, this is an equation that gives us the eigenvalue corresponding to an eigenvector. How so? Basically, the proof is pretty straightforward. If x is an eigenvector, then we know that if x is an eigenvector, we know that ax is going to produce lambda x anyway. Since lambda is a scalar, we can keep it separated, and then x dot x gets cancelled and we get lambda, right? So this equation looks valid, and we can just simply use this equation to find the dominant eigenvector, which is, we got A is 2, -12, 1, -5. This was our original matrix. And x, the eigenvector we got is actually our eigenvector is 2.99, 1.00 dot 2.99, 1.00. You have to understand that this dot is actually dot product of column matrices, right? I mean, dot product of vectors, not matrix multiplication. And we have 2.99, 1.00 dot 2.99, 1.00. If you complete the calculation, you will get lambda equals to a number which is very close to -2.01. So we can just use this equation, but there is a slightly modified version of this algorithm, generally called the power method also, but the power method with scaling. Give me a moment, please. So the slightly modified version is generally called the power method with scaling, but there are also many people who consider this method with scaling the original method. So there are some people who call the scaled version the original power method also. Let's show you how this slight modification is done. Let's choose another matrix now, a 3x3 matrix. 1, 2. You can hear me properly, right?
Yes, sir.
Yes, sir.
Okay, all right. So this is a 3x3 matrix. I am going to share my source material with you in a PDF format right after this meeting. And as I have already mentioned, I am going to provide an assignment problem, and you will get about 30 or 40 minutes roughly to solve that problem. Okay. Let's use x naught equals to 1, 1, 1. So we have, according to the original algorithm, x1 is ax naught. So A is this matrix, x naught is here. If you multiply the two matrices, you will get the column matrix 315. But we are not going to call this guy x1. X1 is a scaled version of this guy. Let's call this guy x1 prime. Then what is x1? Find the element in the column matrix which has the highest magnitude. We have no negative numbers involved here, so we can just consider 5 as the guy with highest magnitude, right? Take that out of the matrix, taking it common. So we have 3 by 5, 1, not really, 1 by 5 and 1. So basically this is, in decimal points, this is 0 0.60, 0 0.20, 1.00. And x1 is this matrix. This is our x1, excluding the 5. I think let's write it in a less confusing way. So let's keep 5 here, and the rest is 0 0.6, 0 0.2, 1.0. So this blue guy is our x1. And in the next iteration, while finding x2, we shall use this x1, but not the x1 prime. So we are going to write a prime here as well. After multiplication, you will get 1, 1, 2.2. Now, again, we are going to find the guy with the highest magnitude, and that is 2.2. Take that out of the matrix, and what remains is 0 0.45, 0 0.45, and 1.00. So technically, in a way, we are making sure that no element of the final column matrix exceeds 1, right? This is what we are making sure in a way. So this guy in the box is our x2. Do the same thing as the original method, just use the scaled version in every iteration. That's the only difference. And if you continue with this process, what happens is at some point, x0, x1, blah, 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 at some point, you get up to x6, which looks like 0. Let's write x5 plus. x5 looks like 0 0.5, 0 0.49, and 1. And x6 looks like 0 0.5, 0 0.5, and 1. And interestingly, x7 is 0 0.5, 0 0.5, 1. So technically, we have converged into something, and this final vector is our dominant eigenvector. But what advantage are we getting using this scaled version? What also happens during the process is, let me use another color. We have 5 here as the scaling factor. We have 2.2 here. If we keep going, then the scaling factor, let's write SF in short. The scaling factors of different iterations are 5.00 in the first iteration, 2.2 in the second, 2.82 in the third, 3.13 in the fourth, 3.02 in the fifth, 2.99 in the sixth, and 3.00 in the seventh. So there is another kind of convergence here, and that converging sequence is formed using the scaling factors, right? And this final point where the scaling factors, sequence of scaling factors converges is the dominant eigenvalue. Now, this method gives us at least 2 advantages. Number 1, we already have the dominant eigenvalue besides the dominant eigenvector after the process terminates, right? We have both. In the original method, in the original power method, we had to use another formula to find lambda at the end. And here we got both simultaneously. And also checking the convergence criteria, that is, when do we terminate the equation? In terms of coding, if you have to check if your vectors converge, you have to do a little bit of calculations here to find the first elements of each. Basically, I can say first element because I have just a 2 by 2 matrix at the beginning, right, to start with. But here we have 3 by 3 matrix. So if you had to check convergence using the elements in the column vector or column matrix, it would be difficult. Maybe we could define some kind of norm, right? Maybe just find the difference of two consecutive column vectors of two consecutive iterations, and somehow define a norm that gives you a real number as output, probably the distance norm or the R2 norm generally we use, right? So, but overall, this makes the thing a little bit complicated. But in this case, the scaling factors are just simple real numbers. So we can just check two consecutive scaling factors and verify if that satisfies our tolerance criteria, right? So this can be an interesting improvement also. So at least two advantages we have discussed. Maybe we have some other advantages as well. But anyway, so what you have to do in today's online assignment is write a code that takes a 3 by 3 matrix as an input, and as output, it gives us the dominant eigenvalue as well as the dominant eigenvector. And you have to use the power method with scaling. I'm going to post the assignment problem within a minute or two after I end this meeting. But so far, do you have any confusion anywhere? Okay, no confusion at all.
Sir, can you please also upload the recording?
Yes, I can upload the recording, but that will take some time. But as I said, I am going to share a PDF with you from where I took the examples. So you will have access to everything I just lectured. Okay.
Thanks, sir.
Okay. Okay, I'm going to close the meeting now. Best of luck for the online assignment.